E.3. 4 questions. Questions from number 7 through number 10. Now, the first question, question number 7. Given a polynomial with the form, here you can see the degree of this polynomial is 4. 4th degree polynomial. The coefficients A0, A1 through A4, here you have the freedom to choose the coefficients. All right, yeah, here. Question, is it possible that one can find a special case? Yeah, here, special case, not a general case. All right, special case, such that the number of multiplications to evaluate this polynomial is less than 4. We know by Horner's rule, we need 4 multiplications, right? Yeah. First, we connect to the Horner's rule. Yeah. Second, we also know Horner's rule is applied on the general case. That is, for any given coefficients, A0, A1 through A4, we can apply Horner's rule. And the number of multiplications, 4 multiplications, guaranteed by Horner's rule, right? Guaranteed. All right, guaranteed. Horner's rule, all right? Yeah, so that's what we get from the Horner's rule. But this question is different. This question, we only need to find one special example. If this example has some special structure, yeah, we are allowed to use some special structure on this polynomial. All right. All right. Next, we need to find an interesting example. All right. Yeah. Here, let me write one. Yeah. Based on my experience, I can write one special polynomial. All right. So let me write this one. All right. 1 plus 4x plus 6x squared plus 4x cubed plus x to the 4th. How about that? Are you familiar with this special format? If you look at the coefficients, it's quite special. If you look at the coefficients, 1, 4, 6, 4, 1. Can you recognize this set of coefficients corresponding to some very famous numbers? Famous numbers, binomial numbers, combinatorial numbers, binomial numbers, combinatorial numbers. Pascal triangle. Do you have some knowledge about Pascal triangle? All right. Yeah. Anyway, so if you do not have that kind of background, I just let you know this polynomial can be written as 1 plus x to the 4th power. Yeah. 1 plus x binomial parenthesis to the 4th power. Okay, 4th power. Yeah. All right. Now this is special structure, right? So we find this special structure. The question, for this special structure, what is the minimum number of multiplications do we need? By repeated squaring here, because fourth power, so here we can use repeated squaring. Repeated squaring technique, right? Yes, okay, yeah. 1 plus x times 1 plus x, the first multiplication. All right, so second, 1 plus x squared times itself, second multiplication. So that's the repeated squaring. So you can see for this special polynomial, we only need 2 multiplications. How about that? Is it better? Is it less than 4? Yes. Yes. Okay. All right, so that's the reason we can choose option A as our answer. Yes, it's possible. Yeah. So that's the question number 7. Next one, so this one. We compare the efficiency of 2 algorithms through their growth functions. Which of the following growth functions corresponds to the faster algorithm? Faster means the order of growth smaller, right? The order of growth smaller. All right, yeah. This is an exponential function. Look at this. A to the n with a greater than 1. This is a power function. N to the constant number d, power function. All right, okay? All right. So here for this question, some students still make their decision using their intuition. All right? By the intuition, it is very likely they may feel n to the 100. It looks like a pretty big number based on their intuition, because the other one, 1.01. This is a number very close to 1, although you raise to power of n, but still it's hard to imagine it can grow very fast for those students using their intuition. Yeah. But the answer is, we know, for this exponential function, we know exponential function dominates the power function. Dominates the power function. And we prove it using the L'Hopital's rule. We can prove it. All right, yeah. We can prove it. Yeah, either way, one way you use the ratio like this. This one you can show it is 0. All right. Another way that, yeah, sometimes you may use this way. You put an exponential function at the numerator, power function at the denominator, you will get infinity. These 2 ways, but either way you can, from these 2 limits, you can get the exponential function has higher order growth. All right, high order of growth. But in this question, we need to select the one with smaller order of growth, not higher order of growth. So based on that, we should pick option B. Yeah. That's our question number 8. Next one, this one. Which of the two functions, log of n and this one, n to the 1/n power, grows faster? Grows faster. Yeah, so if we compare with the previous one, the faster algorithm, right? Yeah, faster algorithm. So its corresponding growth function should grow slower, not faster, right? But here we want to get one function that grows faster. Yeah, so we really need to, pick the right case. Yeah. All right, so here we are familiar with log of n, right? Yeah. At least we have the limit when n goes to infinity, log of n, it's infinity, right? At least we have that. All right. So then the question, the second one, what is the limit of the second function? What is the limit of that? All right. Can we calculate it? Can we calculate it? Right? Yeah. So here, if you want to calculate it, you may need to use some special technique in calculus. You may need to use some special technique in calculus. Here, let me show you. Yeah. All right. And before you use some powerful tool to calculate the limit, probably you may like to convert it to some convenient form. Yeah. Here, the variable n is a discrete variable. If you really want to take derivative, you need to change it to the continuous variable. Yeah. So here, let me just write, let y function equals x to the 1/x power. Yeah, because this time I use x as the variable, I make it continuous variable. Then I can apply powerful tool on it. If it's a discrete variable, I cannot, some important tools I may not be able to use. So that's not very good. Yeah. All right. Yeah. So here you can see the form like that, not easy to handle. A common technique is you take a natural log of this function. So then you will have, by the log property, you have this. Next, you take limit. This time not n. Our variable is x. X goes to infinity. Natural log of y. So this time you will have this form, natural log of x over x. You need to calculate this limit. This limit, you can have a conclusion, right? The numerator is a log function. Denominator is a linear function. We compare this kind of, growth functions many times, right? Yeah. So we can easily get it equals 0. Equals 0. All right. So now you can see equals 0. So y equals What's that? Y equals e to the natural log of y, right? Can you see it? Y equals e to the natural log of y. Yeah? Yeah. So then, this time, when x goes to infinity of y equals e natural log of y. And that limit is 0. So it is 1. All right? So the limit of y when x goes to infinity is 1. X takes the continuous variable, the limit is 1. But then when you take the discrete variable, the limit also 1. Limit also 1. All right. So after our calculation, after our limit calculation, finally we get this limit when n goes to infinity. It is 1. Now you compare infinity and 1. Which one grows faster? One approaches infinity, another approaches 1. So the infinity one is faster, right? Yeah, so very simple. So we have that. Okay, yeah, infinity one is much faster comparing with that constant, yeah, because this goes to 1, so it's a constant. Yeah. All right, so that is question number 9. The last question of this video, yeah, this one. Yeah, this one, here we have a special form. 3 to the log base 2 of n. Yeah. In order to answer this question, because the second form is easy. The exponent is 1. Yeah. The first one, a little hard. So if you can convert the first form to n to the exponent of some constant number d, then we can compare d and 1. Which one is larger? Which one is smaller? Right? So the question is how to do it. How to do this conversion. Yeah. We need to use some special property of log exponential functions. Yeah. All right. First, before we do the conversion, I want to recall a basic formula related to exponent and logarithm. So that is a to the log base a of n equals n. So here, what is the a? The condition for a. First, a must be positive. Second, a cannot be 0. Cannot be 1. All right, sorry. Cannot be 1. So it's a positive, but you cannot put a 1 there. All right? Yeah. Other than that, it is true. So this formula is true. Yeah. It can be proved easily just by the definition of the logarithm. The relationship between the logarithm and the exponential function. You can get this easily. All right? Yeah, yeah. You just take log base a, both sides, they are equal. So if you want to see why this formula is correct, okay? Simple, the fastest way, you just take log base a, both sides, you will see they are equal, right? After you take log base a, both sides, they are equal. So before you take, they must be equal, all right? Yeah, also must be equal. All right. So we start from there, yeah, because this formula is critical for us to simplify expression A expression. All right, so because if we use that formula, we want to write 3 equals 2 to some power. How about that? 2 to some power b. How about that? Because we want to change the base from 3 to 2. Then we will match base 2 and the log of base 2, same base, so we can apply this formula. All right. So our goal, first step, we want to find that constant b such that a equals 3. Yeah. If you take a log base 2 both sides, b equals log base 2 of 3. How about that? Then you can write 3 equals 2 to the log base 2 of 3. Is it one special case of the formula? Here we let a equals 2, a equals 2, n equals 3. How about that? N equals 3. So we have this. That's the first step. All right. Second step, now let us calculate log, this function. When we do calculation, we replace the base 3 by our new form, then log base 2 of n. How about that? Then we know by the property we have this. How about that? Okay? And this log base 2 of 3, it is a constant, right? It is a constant. So we can use another property of log. We put that constant at the exponent of n, power of n function. Power of n function. Now look at the base here and the log base here. They are equal. A case, that tells us the answer is n to the log base 2 of 3. That is the exponent. Okay? That is the d we are looking for, this d. And we also know log base 2 of 3, it is greater than 1, right? Yeah. 2 greater than 3 greater than 2. So log base 2 of 3 greater than 1. Yeah. All right. Here it is 1, d greater than 1. So which one grows faster? The one with higher exponent number grows faster. So here you can see, you need to know math formulas, and also you are able to do step-by-step computation like this. Then you can answer this question. How about that? Think about if you can handle calculation like this one. All right, so let me stop our video E.3 right here.